Alright, today we're going to revisit gravitational energy. So we have our previous version of gravitational energy we called EG, and we had mass times gravity times height. So we're going to revisit this with a little bit of a new lens. So by the end of today, we're going to be able to determine the change in potential energy, potential gravitational energy between two objects with mass. And I will be able to determine the escape velocity of an object in orbit. We're going to hold off on the second part. The escape velocity we'll do tomorrow. Okay, so we'll just start with gravitational energy. I'm going to make this a bit larger here. Come on, there we are. Okay, so there is a gravitational potential energy between any two masses. Okay, normally with their large masses, they're normally spherical in shape. Things like planets and that type of ideas, stars, and that's what most of our conversation will focus on. If the distance between the masses changes, so does the potential energy, which makes sense. So similar to a spring system, work must be done. So if you want to leave Earth's surface, it takes energy for you to leave Earth's surface. As you go farther and farther away, something happens to that gravitational energy. Okay, the force itself decreases, so the effects of the gravitational field on Earth would decrease as you get farther from the planet, but something interesting with the energy happens as well. So if we imagine a spring system, as you try and move farther away, that spring wants to sort of, keep you there, or there's energy stored inside the spring. So if you stretch the spring from left to right and you open it up, there's a stored energy, and then that energy can be changed back into kinetic energy when the spring retracts. So gravitational energy is an attractive energy. We'll see how that plots out in a minute. It's generated by an attractive force, I should say. And so it plots a certain way. If you look over here, this is a force displacement graph, and you can see this little box here. We're going to use the area of a force displacement graph. Gives us the energy involved, the work done. So this is a really weird shape. Okay, so we talked about the force of gravity being defined by this equation. G, M, and M, the top numbers are all constant. So what you see here is a graph of basically 1 over r squared. And that's the basic shape. There's other aspects to it, but that's the basic shape. And so it's not particularly easy to get the area under a curved shape like this without getting into calculus and integration. So what we're going to do is we're going to approximate it with a box. And so what we're assuming here is this box, all of this energy up here, we're going to assume fits into this empty space. And what we're going to do with that, instead of taking something that would be called an arithmetic average, which is what you're used to, we're going to take something called a geometric average. And it's very similar, but it has a few slight differences. If you want to see the full proof, it's on page 285, 86 of your textbook. You're welcome to read that, and I'll ask you to read that again later, just for interest's sake. So the area under the curve, if we're approximating it with a little box, is just the height times the base. So this is traditionally how we find an average. You add things together, divide by 2. But there's also something called a geometric average. And you multiply the two values together and then square root. And so it's a little different. It's going to work a lot better for the question we have here. So it looks like this. The area under the curve, it's going to be, now you'll notice this is the geometric average right here of the force. So F1 times F2 all square rooted, and then this is your base over here. So this is the change in your displacements from R2 to R1, just subtracting them. And so if we replace the forces with our gravitational force calculation involving the masses and the proportional or the constant gravitational constant, it starts to look like this. It starts to get a little busy fairly quickly. Okay, so we're going to multiply those together, get a bunch of squared terms, and now because everything is squared underneath the square root sign, when you actually square root it, you just bring it back down to this size. Okay, so from here we're going to distribute. So we're going to take this big term and we're going to distribute to both of those. And then what happens, and I'll erase this so you can see it first. you get a term that looks like that. And now there's an R1, R2 in both of these. There's an an R1 in both of these. And they simplify. And again, the proof is not so much what you're responsible for, but to see how the parts come together is really important. And you end up with an expression that looks something like that. Okay, so a couple things to notice. The force equation up here, you'll notice has an R squared on the bottom. The energy version of this has only a single R on it. They're very similar, very easy to mistake and swap or use the incorrect one. So please be aware, energy only has a single R on the bottom. Force has an R squared on the bottom. But we're not done there, so we're going to just change the order. So we're going to put R2 in the front, and then we're going to do a little bit of algebraic manipulation. So instead of having a positive here, we're actually going to subtract a negative value. And what that does is it allows me to rewrite it like this. And this is important because now I have the exact same quantities inside the bracket. I have a negative G, capital M, little m, all over an R value. It's the same in both. And I'm just going to subtract those. So that fits with our change in energy is the energy at R2 minus the energy at R1. Okay, and it makes a nice clean formula for us. It's also, we're going to talk a little bit about what that negative sign out front means. Might be a little surprising to you. So these are all the same things. So delta EG, EG2 minus EG1. You could do it with functional notation. And just a reminder that our EG equation now is a negative G, capital M, little m, all over R. Okay, so that's worth a red box. All right, so here we go. Here's the messy part. So if this is our expression for our gravitational energy, depending on our radius or our distance from the planet, from the center of the planet, there's a couple things we can extract from a math class perspective. All of the top values are generally constant. So within a problem, the mass of the planet, the mass of the object you're looking at, and the gravitational constant are all the same. So this simplifies to being 1 over negative r. And if we just think of our math class in terms of what does this curve look like, well, it's very similar to a 1 over x. But it has a negative out front, which means it's a reflection about the x-axis. And so we start to get this red line down here. So this is the graph, or the general shape, of our gravitational energy. Now a couple things will show up in there that might surprise you. It's all negative values. That's probably the most mind-blowing aspect of this, is that all of the values are all negative. And that has some implications on a whole bunch of things. So let's go down here where we have some numbers to actually look at. So this is the curve. This is the graph of our gravitational energy, the G, M, M over R values. And you can see at R1, right here, you'll notice that the gravitational energy at R1, and let's say that's the surface of the Earth, R1, we'll just pull that out of the air. Okay, then, or some distance close to that. It has a negative value. Now, I put in negative 300 just so the numbers are easier. They'd be significantly different, but the key part is that it's actually negative. Okay, and then at R2, this is moving away from the Earth, moving away from the surface. You would have a, ready for this? This is a larger value. Negative 200 is actually larger than negative 300, technically. Okay, so there's actually been a change in gravitational energy here, and that delta EG, and it's done over here for you, it's positive. So as you move away from the surface, your EG increases. And we've done that with our calculation, our MGH calculation. We come up with energies that are generally positive, and we're happy with it. But what we've never talked about before is that your actual energy measurement, of you standing right here on the ground in your classroom or sitting in your classroom, your actual EG value is a negative value. And when you rise up, you climb ladders, you go up in airplanes and those types of things, you are changing to a new negative value. And the only part we've really focused on has been the change in the energy, and it's always been positive, but your actual values are negative. And that's really tricky for some people to digest, which is why we're going to go kind of slow on this today. Okay, so as you raise up, you actually end up with an EG that's positive, but your actual values are all negative. Okay. So if we look at that, and this is a really tricky thought, what if we take an R value that gets really big? So we're at R1, let's say that's our starting point. R2, we're going to make that really large. In fact, we're going to like put it all the way out to infinity. We're going to go super, super far away. And if we do that, this R value on the bottom here gets really big, and this term mathematically goes to 0. But in terms of the gravitational energy, and this is a tough thought, even though the value of this R2 here, this term, is going towards 0, it's actually getting bigger than the other term, because we're starting at a negative value and we're moving towards 0, so technically those numbers are getting larger. Okay, and that's tricky. So this 0, even though we tend to think of that as nothing, the 0 value is actually larger than the R1 term. So as E2 goes to 0, we can see this expression cancels off to 0. We put our double negatives on here, and we get our delta Eg. So the area under our force distance graph, as we go towards infinity with one value, turns into this little expression. Okay. So as an object moves out of gravitational range, the change in potential energy can be simplified to the above. So as you move farther from planets, farther from stars, you can simplify the potential energy down to this expression. Okay. So now near Earth's surface, and this is right out of your textbook, so you can go and read this again a little bit. But near Earth's surface, we do some approximations. So, and some of these are neat from a mathematical standpoint. If we set R1 equal to the radius of Earth, and R2 to the radius of Earth plus some little change, and I mean little change relatively speaking. So when we look at R1 times R2, which was going to be part of our geometric average, that piece, that approximation piece is really important, because R1 times R2 is very similar to just the radius of the Earth squared. Okay, because this delta y is super, super small. Okay, so that's an approximation that we're going to take advantage of. And our delta y is just the change between R2 and R1. And again, we are expecting that to be small. So these are some of the assumptions that we're going to use in our little development here. So we're going to start with the expression we had. We're going to get a common denominator. So to get a common denominator here, this term has to be multiplied by R1. This term has to be multiplied by R2 on top and bottom. We now have common denominators. We can bring the tops together and then factor out the GMM and out it comes. Okay, and they've actually done a little swapping of the order so that we end up with that expression. So that's just a little bit of algebra jumping from this line to this line. Now, R1 times R2 right here on the bottom, we said that's the same as RE, the radius of the Earth all squared. So they're making a simplification. They're also simplifying R2 minus R1 into delta y. And you're going to be like, well, what does that have to do with it? And you can notice the approximation. Well, here's why. Okay, that first term, that GM over the radius of the Earth squared, well, we've seen that before. That's our gravitational, our acceleration due to gravity on Earth. That's our gravitational field strength, if you want to think of it that way. That's our G. So all of the stuff in the highlighter right here, that's our G value, and then we end up with mass times G is our force. Well, if I could take that mass times G right here, and I replace that, now I have mass. Wait a minute, I'm going to find a new highlighter here. Let me get a different color. Okay, this dude right here, all of that comes from this guy. Okay, so that's G, so mg. So I'm going to replace all that's green, goes right there. Okay, now that's significant, and you've actually been working with this formula for a while now, since grade 11, because that formula is Eg equals mass times gravity times h. So the formula you've been using since grade 11 is a simplified version of this larger context idea that we're developing on this line. Okay, so we can still use the shortcut, the simplified version for objects closer to Earth. We'll just use this formula right here. But when we have objects that are moving away from Earth or farther away from Earth, then we have to jump up to the more the larger problem, which is this guy right here. Okay, so this is a one quick example, and then I'm going to stop. So what is the change in gravitational potential energy of a 64.5 kilogram astronaut lifted from Earth's surface into a circular orbit of altitude 440 kilometers? So a couple things you don't like right away. I see kilometers, that makes me a bit nervous, so I might change that. You can see over here when we're finding our R2, they've got the radius of the Earth plus that in kilometers, but then they make the change, and we get everything into meters. So you have a radius, a second radius of 6.82 times 10 to the 6. Your first radius, 6.38 times 10 to the 6. We're happy with our mass of our astronauts in kilograms, and our gravitational constant, as always, is the same, and then the mass of the Earth is given. So pause it there, and then we'll take a shot at filling in the numbers and see what you get. Okay, so you've had a chance to try your numbers. So I have the short version here. I have my expression. I factored out the GMM because I don't want to type that in several times, so I factored that out. And then I punch in my numbers. And what we should notice, and I've just highlighted it here for you, this term right here outputs a negative value. And that's important because that negative value, when we multiply it through, it combines with that negative value, and we end up with a positive value. And so we should get some positive change because this is a delta Eg, something moving away. We have an increase in our gravitational energy, which makes sense. That's what we're expecting to get. Okay. So even though the values for the astronaut's gravitational potential energy, if you calculated them separately, you would have had two negatives. But the change from one negative number to the other is an actual increase, so it's a positive value. And that's a really big thought. Tricky. So oops, I'm going to just jump down. We're going to skip this part, and I'm going to get you to, oh, where did I put that? I lost my equation. There they are. Okay, so I'm going to stop there. We'll leave the next part. If you could just take a read of the chapter, that would be awesome. And then we're in person. We'll do the follow-up on that, but it'll be much easier if you've read it once. And then if you could just try the 3 questions on 287 and leave these for the next day.